So let's get started on question 8. It says consider a continuous random variable whose probability density function is cx to the negative 3 for x greater than or equal to 1 and 0 outside this range. And we want to find c. So if you recall, for any valid probability density function, f of x, we have the property that if we integrate from negative infinity to infinity over this density function, we should get 1. Right? And so we can use this property to be able to solve for c. So we know that the density is cx to the negative 3 for x greater than or equal to 1 and 0 outside this range. So we only need to consider or integrate over the places that this density function is non-zero. So it's non-zero for x greater than or equal to 1, or when it's 1 to infinity. And if we integrate this, because this is a valid PDF, we should get 1. So let's try to evaluate this integral and solve for c. So first I'm going to take this c out of the integral. And then find the antiderivative for x to the negative 3. That's just negative 1/2 x to the negative 2. I'm going to evaluate this at infinity and 1. And if I evaluate x at negative infinity, or x at infinity, it'll be evaluate to 0 because 1 over infinity squared is 0. And then if I evaluate x at 1, this will just be negative 1/2 times 1. And I'll get that this is equal to half c. And I want half c, or my resulting integral, to be equal to 1 since it's a valid probability density function. And this means c is equal to 2. Okay. So now let's get started on 8.2 part A. So it says consider random variables xy with joint density fxy equals cxy for xy in 0, 1 and 0 outside that range. And we want to find c in this case. So if you recall, for a valid joint density, right, if I integrate over all the possible values of x and y, I should get 1, right? Because this is a valid joint density. So in order to solve for c, I should use this fact right here. So if I integrate over all the possible places where the density is not 0, so that's when x and y are both between 0 and 1, and integrate cxy dx dy, this should give me 1. So I'm going to pull out the c from the integral. And then I'm going to evaluate this inner integral. So the antiderivative of xy with respect to x is just half x squared y. And I get, so if I evaluate this, if I evaluate x at 1, this is equal to half y. If I evaluate x equals 0, it's just 0. And then now if I evaluate this integral, the antiderivative of half y is 1/4 y squared. Evaluate this at 1 and 0. And then I should get, if I evaluate this at 1, I get 1/4. And I evaluate this at 0, I get 0. And this gives me 1/4 times c. And so if I evaluate this joint integral, or double integral rather, I should get 1/4 c, and I want 1/4 c to be equal to 1 because it's a valid joint density, which means c must be equal to 4. And Okay, so now we're going to look at 8.2 part B. We have this joint density from the previous part, and we want to find the probability that the absolute value of x minus y is less than or equal to a half. So when dealing with these types of problems, it helps to draw out the region we want to integrate over. So if I have, x and y, and I want to draw out this particular region, so I know that both of them take on values from 0 to 1. So my entire probability space is just this square. And I want to find the region where x minus absolute value of x minus y is less than or equal to a half. And if you think about what this means either x minus y is less than or equal to a half, or y minus x is going to be less than or equal to a half. So how do we plot these regions? Well, first I can simplify this into y being greater than x minus a half. So if I draw the line y equals x minus a half, I get this line right here. So I have the point half comma 0 here and 1 comma half. So this is the line y equals x minus a half, and then I can simplify this equation right here to be y less than or equal to x plus a half. So I can draw the line y equals x plus a half. So it has the point 0 half and half 1. That's this line right here. And if you notice, I want everything basically above this line. So this line is y equals x minus a half. So I want everything above this line and everything below this line right here. So everything below the line y equals x plus a half. So I basically want to find this region right here. And if you notice, this region is quite difficult to integrate. It's a hexagon-shaped region. So what I can do instead of integrating over this region is to consider the complement. And if you notice, the complement is basically these two triangles right here. So these two triangles should be easier to integrate over than this hexagon. So one strategy is to find the complement instead. So the probability of this complement should just be, we can get this by just integrating over these two triangles. So let's just do that. So if I integrate over the two triangles, what should be the bounds of my integral? So if you look at y, it varies from a half to 1. So I can write that out, 1/2 to 1. And if I look at what x varies to, well, x, if I basically draw this line at y equals y, y equaling some value y, I want to see what x can range to. So x, you can see, will start at 0, and it'll go up to the intersection at the line here. And where is that intersection? Well, that intersection I can get from the equation of the line, y equals x plus half. This means x will equal y minus a half. So this point right here will just be x will just be y minus half. So x will range from 0 to y minus a half, and I integrate over the joint density dx dy. So I know the joint density is 4xy and so I can start integrating. So I take the antiderivative of 4xy with respect to x. I get 2x squared y, and I evaluate this at y minus a half, 0. And so if I evaluate this at y minus a half, I get 2 times y minus a half squared times y. And if I evaluate this at 0, I just get 0. And so I'm going to pull the 2 out and expand the squared term. So this is just y squared minus y plus a fourth times y dy. And I can multiply the y to get y cubed minus y squared plus 1/4 y. And I can take the antiderivative of this, which is 1/4 y to the fourth minus 1/3 y cubed plus 1/8 y squared, and evaluate this at 1 and then a half. So this is just equal to 2 times 1/4 minus a third plus an eighth minus, and if I evaluate y at a half, so 1/4 times a half to the fourth, so it's just 1/4 times 1/16 minus 1/3 times y cubed, so if I evaluate it at a half, so it's 1/3 times a half cubed, which is 1/8. And if I evaluate y at a half here, I get 1/8 times a half squared, which is 1/4. So I get 2 times 1/4 minus a third plus an eighth minus 1/64 plus 1/24 minus 1/32. So I have a bunch of these fractions, and I'm going to just try to combine them bit by bit. So I'm going to first combine the 1/4, the 1/8, the 1/64, and the 1/32. Because they all can be, I can turn them into fractions with 64 on the denominator. So have them have a common denominator. So this is just 16/64 minus a third plus 8/64 minus 1/64 plus 1/24 minus 2/64. And so 16 plus 8 is 24, minus 1, 23, minus 2, 21. So this is just 21/64. And then minus a third plus 1/24. And then I can convert this into a denominator of 24. So this is just 8/24 plus 1/24. And I get 2 times 21/64 minus 7/24. So now I want to combine these fractions. And if I iterate through the multiples of 64, I see 192 is the first. So I want to combine these fractions. So I want to find a common denominator. And I see that 192 is a common denominator, or is a multiple of both of them. So 192 is 3 times 64. So this fraction can be turned into 63/192. And 24 times 8 is 192. So I can multiply the top and the bottom by 8. And I get that this is equal to 2 times 7/192, which is 7/96. So the area, or the density, or the probability in this first triangle over here is 7/96. So now, so before we find the probability in the second triangle, we can actually see that it's the exact same as the first triangle. And the reason for that is, consider this point right here, right? X1, Y1. So this point has a density of, so if I plug it into the formula, this point has a density of 4x1, y1, right? But if I look at the reflection across the line y equals x, so this line y equals x, I can see that this point right here will have the same coordinates, but just flipped. So this point right here will have the coordinate y1, x1. And you notice that this point, what's the point of this density? It's the exact same, right? This point at y1, x1, which is the reflection of this point across the line y equals x, has the exact same density. And we can see that basically for any point here, I can find a matching point on the other side of the other side reflected across the line with the exact same density. And I can do this for all the points, and we can see that essentially the mass here is identical to the mass here, because all points of mass here get reflected and accounted for here. So in fact, the probabilities within these two triangles are identical, but we can, try to verify for ourselves that's the case. So this use of symmetry across the line y equals x allows us to save some time, but we can evaluate the integral just to be sure. So for triangle number 2, we can evaluate it just for completeness. So if we look at, again, y here goes from 0 to this point, which is 1 comma half. So it goes from 0 to half. And again, if I draw the line here, dotted line here, if I fix a value of y equals y, I see that x starts at this intersection with y, and it ends at 1. Where's the intersection? Well, if y is equal to x minus a half, that means x is equal to y plus a half. So the intersection must occur at y plus a half. So this means that x starts at y plus half, and it goes all the way to 1. So if y goes from 0 to a half, x goes from y plus a half to 1. And again, we integrate over the joint density. So we can plug in the joint density, which is 4xy. And I can take the antiderivative with respect to x. So this is just, again, 2x squared y. Here I evaluate it at 1 and y plus a half. And this should get me the integral 0 to a half. So if I evaluate this at 1, I get 2y. And if I evaluate this at y plus a half, this should give me 2 times y plus a half squared times y dy. So now I'm going to take out this factor of 2. And I'm going to expand this square here. So it's going to be y squared plus y plus a fourth times y dy. And then I can simplify it to be y minus y cubed minus y squared minus 1/4 y dy. So now I'm just going to take an extra simplifying step, and I'm going to merge these two to be 3/4 y. And now I'm going to just take the antiderivative. So 3/4 y is just 3/8 y squared minus 1/4 y to the fourth minus 1/3 y cubed, and evaluate this at a half and 0. So if I evaluate everything at a half, this is just 3/8 times a fourth minus 1/4 times 1/2 to the fourth, which is 1/16, minus 1/3 times 1/2 to the third, which is 1/8. Oh yeah, and then if I evaluate this at 0, I just get 0. So now I have this is equal to 2 times 3/8. So 3/8 times a fourth, so this is 3/32 minus 1/64 minus 1/24. And I can simplify this fraction, or I can try to combine these two fractions. So this is 6/64 minus 1/64 minus 1/24, which is 2 times 5/64 minus 1/24. And again, I know, remember 64 and 24, the least common multiple is 192. So I'm just going to write it on a new line. So I multiply the top and bottom by 3. And I can multiply the top and bottom by 8 here. to again get 7 times, or 2 times 7 over 192, which is equal to 7 over 96. So again, the area of triangle 2 is, so this triangle right here is equal to 7 over 96. So we see that, you know, the area of 1 plus the area of 2 is equal to 7 over 96 plus 7 over 96, which is equal to 7 over 48. So all in all, this gets us the complement, which is probability that absolute value of x and y, x minus y greater than or equal to half. This is now equal to 7 over 48, which means the probability that we want, which is x, absolute value of x minus y, less than or equal to a half. This is equal to 1 minus 7 over 48, equal to 41 over 48. And that's our final answer. So you can see here, you didn't have to do the extra work of finding the probability of triangle over triangle 2, again, because of the whole symmetry argument. So just to reiterate, at any point in one of the triangles, that point's density is accounted for in the other triangle, which is basically the point on the reflection of the line y equals x. So because of this, you know, you could have saved yourself some time by basically saying that this probability here is the exact same here, so you'd only have to do one calculation. But we did both here just to be complete.